Welcome back. In this video, we're going to be looking at Momentum, Worksheet 1, Roman numeral number 3, the conceptual question. Let's get into it. If a semi-truck, so big, large vehicle, and a small smart car traveling at equal speed have a head-on collision, that would be terrible. A, which vehicle will experience the greatest force of impact or during impact? B, which will experience the greatest change of momentum? And C, which will experience the greatest acceleration. All right, so let's go ahead and get into this. First, let's draw a picture and identify what our action is here. So here we're talking about the collision is our action there. So I'm going to do a before and after picture of both before that collision and after that collision. And we're going to be looking at then the change in velocity before and after, the change in momentum before and after, and the force then maybe during that thing. And you could actually draw a third picture of like during the collision there as well. And maybe that'd be smart in this case. Actually, that probably would be smart in this case. I'm going to go ahead and do that. So I'm going to do like the during. Just because it asks for the force, and so I'll make that one a little bit smaller. Before and after. Okay. So let's get into drawing a big semi here. So let's have the gigantic semi, maybe show the whole thing. The big semi here, usually have two wheels there, and then the cab part here. And they usually have two more wheels right there. This little door. It's not a little door, it's a big door. Little smokestacks coming out. That's a really big front there. That's okay. And then, so they're going to the right. This little smart car, oh gosh, what do they look like? They're like really steep in the front and they just like stop in the back there. Smart car is is the only car that I know that has 3 lugs to hold that wheel on. Those are the nuts. That's what it's called. It usually has very minimum 4, and usually it has 5 or more. They got 3. Anyways, okay, so this guy's going to the left, and the semi-truck is going to the right. Let's go put that in. We see that this guy is going beforehand, moving that direction, and this guy is moving that direction. And it's the exact same amount, so I can label it the exact same variable V naught for both of those guys. Now, not everything is equal. The velocity is equal, but we know that the masses most definitely are not equal. We got a mass of this truck there, T for truck, and then the mass of this car here, we'll do C for car. Okay, great. And we should probably put the ground on there as well. They're driving on something. Okay. So now these guys are going to run into each other, so I'm going to go ahead and speed up this thing because you can pause this and such whenever you want. I'm going to go ahead and copy some of this stuff and move that over so I don't have to keep redrawing it, and I didn't mean to do that. So we'll paste that back down there and move that back over. Oh, and I missed a wheel. Like that? It must have been like that. No, it wasn't like that. It wasn't that far over. Oh, goodness. Oh, goodness. Let's try this one more time. Okay. If I copy that and paste that, oh, I didn't get the whole thing. I'm going to scale that down and redraw the rest of that. Get the ground down there. Get that little vector out of there, and then move this guy over. So during that collision, and then we'll do that after the collision there as well. Okay. So during that collision, clearly there's going to be like some like crumpling going on there, and crumpling of that little smart car. There's not a whole lot of crumple going on or able to go on in that smart car, as opposed to like most other vehicles that have a much larger front end. Hey, that brings up another question. I wonder why vehicles have a long front end to them. Anyways, let's come back to that one. Which vehicle will experience the greatest force of impact. Well, let's look at the forces going on for these guys here. Well, truck runs into car. Is truck going to put a force on the car? And you'd say, oh, yeah, absolutely. There's going to be, what type of force would that be? It'd be some sort of normal force on the car by the truck. Okay. Now, on the truck here, I'll do my dot on the truck. On the truck there, would the car put any force on the truck? And if you're not sure, go, would the truck running into the car, would the car impede the truck's motion some? Might it slow down a little bit? And you'd probably say, well, yeah, sure, it's got to slow down like a little bit because it's running into things. Well, that's evidence that it's accelerating, and the only way that you make anything accelerate is you must have unbalanced forces on that thing. And that's supposed to be a summation sign there. It got a little bit sloppy. And so then that means that I must have some unbalanced force on this truck here, and the car is producing that. So that's the normal force on the truck by the car there. Okay, how do these forces compare to one another? Well, I look at that and I go, okay, truck pushes car to the right. Car pushes truck to the left. Well, hold on, that sounds like something else we've heard before. That's like if I said the truck was A and the car was B, that's like A acts on B. Therefore, B must also act on A. That sounds like what law? That's Newton's third law. And we've seen before that that has to always be the exact same. And it is. It actually truly is in this case as well as any other case. We've never actually seen any violations to Newton's third law yet. Okay, so that means that both of them get the exact same amount of force. Even though you might say the smart car is going to get demolished in this and the truck would probably be mostly fine. And I would agree with that if we actually witnessed this horrendous crash there. But no matter which one, quote unquote, wins or which one is, quote unquote, stronger, both of them will get the exact same amount of force on them. And we did that in the lab, and this is a pretty extreme case here. We did that in the lab of different masses on those four sensors there and then accelerating those along. And we always got the exact same amount of force in both of those sensors there. And this is the same thing going on here. Which will experience the greatest change in momentum? Okay, well, let's think about this from momentum. Let's think about the momentum beforehand, way over here on the left-hand side. And let's do red for the truck there. So the momentum beforehand of the truck, so I'll put PT at the beginning there for the truck. And we'll do purple for the smart car there. So the momentum of the car at the beginning there. Well, we know that the momentum is just the mass of the car times the velocity of the car at the beginning. And same thing going on with the truck there as well. That's the mass of the truck times the velocity of the truck at the beginning. Well, let's think about this. I got one going to the right and one going to the left. We'll just assume that we have the normal Cartesian coordinate plane because there's no good reason to change that. So we'll say to the right is positive, to the left is negative. That means that this truck here is going to have some positive velocity, so it's going to have some positive momentum. And then this smart car over here is going to be going to the left there. Well, that means it's going to be a negative velocity and therefore going to have some negative momentum. Okay. Now, when I add those together, when I go and add these two together to get my total momentum at the beginning there in the before state, notice it's in this before column here, will that be equal to 0? Well, they're the same velocities, right? But they're not the same mass. Okay, so then which one's going to have more momentum at the beginning? The truck going or the car going? Yeah. Sure, the truck is going to have more momentum. It's got more mass going the exact same speed. And even without any numbers or even probably being in physics, you would probably say that the heavier object that's going the same speed is going to have more momentum going forward. It's got more motion going forward. And I would agree with you, and that's actually very true. So then when I add these two things together, I'm going to get some positive or negative quantity. I'm going to get something that is like positive here since the red one is bigger than this negative purple one there. And so it means that I have an a total amount of momentum that's going to the right in this case. And so that's like on our coordinate plane there. Okay, so then, wait, hold on a second. The only two things interacting here are this truck and the car. I agree that the ground is holding them up there, but we're not like transferring momentum to the ground or anything. We're rolling freely on these wheels here. So then, okay, great. So if I'm making my system, both the truck and the car, maybe I should write that out somewhere. So my system here is both the truck and the car. And how did I know that I was already doing that? Well, I looked at this and I said, I'm adding both of those momentum together. And so then therefore I'm calculating the amount of momentum of my entire system here because I'm literally adding them together. So then my system must be both the truck and the car. So now I go and I'm going to, well, let's do that during the crash, or let's do it after the crash. Usually we don't actually do it like during the crash there. I just did that so we could look at the forces directly during the crash there. So let's go ahead and let's skip over and do it to the ending, the after case here. So they run into each other. The smart car gets inevitably destroyed. This is the smoke coming out. The truck, would the truck still be going to the right, do you think? Yeah, probably. It's got tons of motion going forward, and so it's going to take a huge amount of force to be able to stop that motion. More force to stop that motion than the car, you might say. Hold on, that's not entirely correct. It would be like more force over a greater distance, to slow that thing down. We're thinking about energy there. Or in this unit here, it would take like more force over a greater amount of time than the smart car to slow down. Well, let's think about that. Well, hold on. The force of both of these things is exactly the same. Now, if I was an innocent bystander here, and I was going to time this, let's see if I can draw a stopwatch. I was going to go and time this thing, and I had the stopwatch, and this is like the old-timey stopwatch that like goes around there, and I timed this collision of when they were actually like actively colliding into one another. They might like bounce off each other afterwards, but when they're actively like colliding and maybe the little bit of front of this car is crushing and maybe the truck front end crushes and dents a little bit on the bumper there, how long that collision of like crushing those bits takes? Would I get 1 or 2 times? Would it be the same amount of time for both the truck and the car when they're colliding, or would there be 2 different times? You'd say, yeah, it's just one collision, so I can only measure it one way of when they start to hit and when they, stop hitting or stop crushing into one another. So then it would just be one time. Well, hold on a second. We know, let's think about this from a slightly different perspective here. We know that that some force, let me do this in the beginning, the during stage. We know that some force through some time there is equal to the change in momentum of something. Okay, so now let's do that in 2 different ways. Let's do that for the truck here. So the truck gets some negative force, you'd say, because it's to the left there. So that means that it's going to have some negative change in momentum. Oh, well, let's think about that. Do you think the truck would slow down? Do you think its velocity would decrease after it runs into this thing? Sure, yeah, we said that before. Oh, and so then if it's got some positive momentum beforehand, it would then get some negative change in momentum, meaning that this thing would get a little bit smaller. Oh, which means not the mass would change, well, maybe some parts would fly off, but really the velocity of that truck would slow down there. Okay, well, let's think about that from the car's perspective then. If I look at that from the car's got some force on there and some time, and it would have some change in momentum. Now, let's compare the forces. Are the forces the same or bigger or smaller? Well, they're the same, we said. It's the Newton's third law there. So that force is the same on the car. Now, the force is to the right, so this is going to be a positive thing then to the right and going to give you some positive change in momentum. Let's think about that for the car. Car's got some negative momentum because it's going to the left there, and so if I add something to that, it becomes less negative, more positive. So then I go, okay, great. During this collision, is the car not going to be going as fast to the left afterwards? then you'd say, oh yeah, it's clearly reasonable. Probably this car is going to get ejected to the right-hand side after this collision, and I would probably agree with you. Okay, so that means that, yeah, adding momentum to the original negative momentum of the car there might then make it go to the right. It would have some velocity that's positive then afterwards, a momentum that is positive then afterwards. Okay, so we think about it slightly differently there, but it's really the same. Now let's look at this in the after state here. So now let's color code this right. So now I have the momentum of the truck, and I can add that to the momentum of the car there, and these are the after states. And so that's going to be the mass of the truck. We realize that parts and such can fly off in reality. Let's go ahead and let's assume that it's the same mass for the truck here and the same mass for the car here for simplicity's sake. That's going to be the velocity of the truck then afterwards, and we're going to add that to the mass of the car there times the velocity of the car. Now when I add those together, I'm going to have to get some positive bit just like I did before. Now you told me that this truck here is going to be going slower afterwards because it ran into something. So that means that this is a little bit smaller. So if that velocity is slower, that means, let me offset that a little bit. If this is slower, that means that this whole quantity here must be smaller as well. Now, if that's smaller, but it has to equal the exact same values over here because the momentum beforehand must be equal, let's write that there, the momentum beforehand must be equal to the momentum afterwards if we've included everything in our system and there's no external forces there, which we identified before, that the only motion that's transferred here is between the truck and the car. So then the momentum before must be equal to the momentum afterwards, or another way to say it is the change in momentum of this entire system or of the entire universe here, you might say, is equal to 0. That when I add up the after bits here, it's got to be equal to the same as the beginning bits. Okay, well now if this positive bit is smaller and it's got to add up to be the same positive bit, well then how can I possibly mathematically make up for that? That means that this thing must be a positive quantity, which means that this thing is going to be some positive quantity, which means that this car must be going to the right there. That's supposed to be a V. This car then afterwards must be going to the right. Yeah, it gets like ejected to the right there. You could probably envision that in your head, and you could probably YouTube a bunch of different crashes like that. Yeah, it would get ejected to the right. And notice that the physics here, the momentum actually clearly shows that that must be true. And so then here, without doing any numbers, we can see that this one gets smaller, and so then this one must be that difference there. It'll be that positive bit, but that difference from the original total momentum there. Okay, so then, how did this happen? Let's talk about it, how momentum transferred here. Truck was moving to the right, had a huge amount of momentum because it had a huge mass. Little car was moving to the left, had some momentum, but a lot less because it had a much smaller mass, even though they're both going the same speed. They run into each other, they push on each other, and then afterwards here, the truck now isn't moving as fast to the right. Where did that motion go? Oh, that motion, or that momentum, went into the car. That truck's motion, or momentum, slowed down, got smaller, because now the car has more motion moving to the right. It changed not just from going to the left to not going to the left, it changed from going to the left, now reversing totally, and moving now completely to the right-hand side there. Probably not as fast as the original velocity there, but we'd have to put in numbers to actually find that calculation there. Okay, so now the last bit here, this is all about momentum here. The last bit here, so which one will experience the greatest change in momentum? Well, it's going to be the same change in momentum. So how do I know that? Well, we know that. Well, I actually proved that over here. I just didn't say that. Here, it's the exact same amount of force for both of these guys, and we said there's a lot of arrows all of a sudden, and we said it's the same amount of time for both of these guys because we would time just the one collision. So now if that's true, then the change in momentum for both of these guys must be exactly the same. Hopefully you can kind of see that. That one's going to be negative and one's going to be positive, right? That's where that negative from the force came from. But it would be the exact same amount. So the change in momentum, you might say, of the truck is then going to be equal and opposite of the change in momentum of the car. Truck slowed down. Now it's not moving to the right as fast, and now the car is moving to the right way, way faster than before. So much faster that it wasn't even moving to the right before. Okay, so they're going to have the same change in momentum, but which one is going to have a greatest acceleration? Well, there's a couple ways that you can go about and look at this. First, let's look at it by force, since we've been doing that for so long now throughout the year. If I look at that through force, let me write it like this. We said that let's do it in color-coded like I did before. Take red for the truck there. We said that there's this force on the truck through some time there, and we said that that was equal to the force that's on the car through some time there. We said that the force is the same and those times are the same there as well. Well, if the times are the same, well, do I want to do it like that? Maybe I don't want to do it like that. Well, I can't. Let's keep doing it like that. Yeah, let's keep doing it like that. So now, if I think about that, I go, well, that force there, I know that if I add up all those forces, it's always equal to m times a. That's always true. And in this case, is that all of the forces? Well, it's the only force in the horizontal dimension there. So this is the sum of the force in the x dimension there. So let's go ahead and let's sum up the force in the x dimension, which is just this normal force that's on the truck and the normal force that's on the car by each other. And now if I go and do that, I could go and I can replace this F there with m times a. Now that red one represents the truck there, so that's the mass of the truck there. And don't forget that one of them is negative here, and we're just carrying that through, times the acceleration of that truck there. So I'm going to put a T on that acceleration to make sure that I remember it's from the truck there. And now I'm going to multiply that by the time. Now I'm going to change the color of the time there, because the color of the time, let me change that to blue, is the same for both of them. So let's try and keep that organized there. So I'm going to do the same thing. Force is mass times acceleration for the little car there. The little car is a small mass, and then I don't know what the acceleration is going to be, but we'll find out. And then multiplied by the time, we'll do the time in blue there because it's the same. Now if it's the same on both sides there, can't I just cancel out those guys because I can divide by delta t there? Yes, I can. So now let's keep going through this. I have the mass of the car times the acceleration of the car is equal and opposite of the mass of the truck times the acceleration of the truck there. So now I want to compare these accelerations here. Well, let's do it visually and see where we get. I already kind of did that, and I said that the mass of the truck is really big, and so let me amplify that a little bit more and say that the mass of the car is really small in comparison. Now, if I multiply these things together on the right side, and I multiply these things on the left side, I got to get the same value, except one of the accelerations can be like a negative value, and that's what's going to take care of this negative sign over there. So that means that if I take a huge mass on the left side and multiply it by whatever acceleration it gets, the acceleration of the truck you'd probably say is pretty small, right? It's going to be a lot smaller than the car, I would assume. I'm going to take some mass, multiply it by some acceleration to get something. That mass is huge, though. Over here, I take a really small mass, I got to multiply by something, and it's got to get the same value there. That means that this acceleration can't be the same size as the truck. It's got to be really big in comparison to that truck there. Oh, and so now I can visually see that the acceleration of the truck must be a lot smaller than the acceleration. The acceleration of the truck must be a lot smaller than the acceleration of the car if the mass of the car is a lot smaller than the mass of the truck. What's a more mathematical way to show that? Well, we'll look at it as in terms of ratios. I'll divide both the mass over to one side and the acceleration over to one side. So I'd have the mass of the truck divided by the mass of the car is now equal to the acceleration of the car over the acceleration of the truck. And so now I just look at this ratio on the left side here and go, hey, the mass of the truck there, let's do that visually again. Mass of that truck is going to be gigantic, and the mass of the car is going to be really small. So now I have a ratio that's going to be really, really big. that means that over here on the right-hand side, that ratio must be really big as well. Let's do that visually. The acceleration of the car, we said, is probably going to be huge, and the acceleration of the truck would be really small, and that would give me it would be the exact same ratio mathematically. Okay, so now we know that this blue statement over here is true, that the acceleration of the truck is much, much less than the acceleration of the car, and that's true if the mass of the truck is much, much less than, is much, much greater than the mass of the car. Okay, cool. So it's just looking at this ratio here. And don't let that negative trip you up there. That negative is, the acceleration. Let's look at the accelerations. The acceleration of the truck's moving to the right, and then it slows down. So the acceleration of the truck there must be to the left there. Car was moving to the left, now is going to be moving to the right afterwards, so the car is going to be accelerating that way. So this is the truck, that's the car. And so, the truck's acceleration is going to be negative, and so that's where this guy comes out to be a little negative there and takes care of that negative over there. Cool. So, which vehicle experiences the smallest acceleration? Well, look at this. That's the heaviest vehicle. So if you were in some crazy situation and you had to run into some vehicle, you're going to choose the heaviest vehicle? No. You're going to choose the lighter vehicle. And the heavier vehicle, the heavier object that you run into, the greater the acceleration on your car, and therefore you know it's not going to go so well for you. Think about an extreme example of like a train. Never get in a situation where you're stuck on the tracks somewhere. Always give somebody extra time in front of you and extra space in front of you so that if they had to stop, because somebody's turning to the left or something like that right after the train tracks, that you don't have to then stop on the train tracks. Be smart about it. Don't be in a rush all the time. Because if the train came and ran into you, now think about that ratio of mass difference between the T train and your car there. Then think about the acceleration differences there. And then you go, man, I can really hurt myself if I accelerate too quickly. If I jump off, this a tree branch that's too high and I hit the ground, going really fast, I might accelerate really quickly when I hit the ground and it stops me so quickly that I might break my leg or something like that. So the bigger the acceleration I have on me, the more I might be able to hurt myself. Yeah. And so same thing is true in collisions. Collisions of any objects that can move. It's a little bit different when you run into like a brick wall, but it's really the same thing. It's just the brick wall is attached to the earth and the whole earth is moving. So that mass is like, gigantic. And the acceleration of the earth then is like minuscule. Okay, that's it. Hope you enjoyed that. Have a beautiful day.